Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss one of the transport phenomena, that is viscosity, means transport of momentum. Let's begin. What is viscosity? The phenomenon of viscosity occurs in a gas when different layers of the gas moves with different speeds. So here let us consider a gas which is moving in parallel between the layers AB and CD. We take the coordinate plane OX, OZ. This is the Z axis. Layer as A, B, C, D. Gas which is moving parallel layers between the horizontal planes AB and CD. Here AB line means a plane passing through that of AB. Let us consider a plane here which is passing through that of line AB, and the plane passing through the line CD, that is the horizontal plane passing through that of line CD. These two are parallel to x axis. Suppose that motion takes place parallel to x axis. The motion of the gas molecules takes place parallel to x axis, and let the velocity of the layer of gas in contact with the plane AB will be 0. Means the velocity which are contact with that of layer will be 0, and the velocity increases as we move towards the plane CD. The velocity of the layer which is contact to AB will be 0. Gradually that velocity increases as we proceed from AB to CD. Let us consider an intermediate plane LM. We take an intermediate plane. This is the intermediate plane LM is the intermediate plane here. This is the plane which is passing through that of line LM, that is the intermediate plane between AB and CD. LM, the intermediate plane LM, the velocity of that of layers of gas above to that of intermediate plane LM is greater than the layers of the gas below it. Since here the velocity associated with that of layer AB will be 0, gradually it will be increases towards the CD. Here we consider the intermediate layer LM. So above the intermediate layer LM, here the molecules possessed the velocity will be greater as we compare the lower portion of that of intermediate layer LM. Again, the layer above LM exerts the tangential force on the layer below LM. That layer exerts the tangential force to that layer lower to that of LM, that tending to accelerate in forward direction. Means while the layer below LM, this portion exerts an equal force on the layer above Lm, which is tending to retard it backward. This is the forward, its reverse force will be backward. Thus, these forces tend to reduce the difference in velocities of the layers on the two sides of the planes. There will be the velocities on that of upper side of the Lm, there will be the gas particles having the velocity the lower side of Lm. The relative velocities in between the upper and lower sides of that of Lm, the difference in velocities of the layers on these each sides of that of plane, this property of gas is known as the viscosity, that particular property which is known as viscosity. As we say, viscosity is the phenomenon occurs in gas when different layers of gas moves with different speeds. So, here the upper half of that of Lm moves the higher speeds as comparison to that of lower half of that Lm. There will be the difference in velocities between the upper and lower half of that of Lm. That difference in velocities is considered to a phenomenon that is known as the viscosity. Now, since the molecules of the gas above Lm have greater horizontal velocity, hence possesses greater momentum in horizontal direction than those of below it. Upper molecules have greater velocities and greater momentum also as comparison to that of lower half. On account of thermal agitation, here we take the term thermal agitation. What is that of thermal agitation? Means there is a transfer of molecules of greater average momentum in downward across Lm and molecules of smaller average momentum upward across that of Lm. There will be the molecules having higher momentum that to that of lower momentum, and here the molecules have lower momentum that to that of upward section due to the phenomenon of thermal agitation. Thus, what happened here? The layer of gas above Lm suffers a loss of momentum. Here a loss of momentum occur. Here a loss of momentum in case of above Lm, loss of momentum. So, what happened here? According to Newton's second law of motion, a loss in momentum gives rise to the retarding force, that gives rise to the retarding force. Retarding force, and the lower portion of that of Lm, which is the gain in momentum, that gives rise to an accelerating force. Here the lower portion, here is the gain in momentum, that is the accelerating force. The accelerating force. Above portion, that is the loss of momentum, which is retarding force. The lower portion, that is the gain in momentum, which is the accelerating force. Here the retarding force, this is the accelerating force, this is the loss of momentum, that is the gain in momentum. This is the upper half, that is the lower half of Lm. Therefore, the layer above Lm experience a retarding force in backward direction, that is retarding force in backward direction. Backward direction, whereas the lower below Lm experience an accelerating force in forward direction. Here is the accelerating force in forward direction. This gives rise to the viscosity of gas. All these phenomena, all these processes are under due to the viscosity of gases. This is all about the viscosity of gases, how the viscosity phenomenon is proceeds or occurred in that of particular case as we considered. Now, we have to move towards the mathematical analysis of these things. Let we consider, let small n be the number of molecules per unit volume and C bar is the average velocity due to the thermal agitation with which they are constantly moving in all directions. N is the number of molecules per unit volume and C bar is the average velocity due to that of thermal agitation. Suppose that 1/3 of the molecules are moving in each three directions parallel to three coordinate axes. 1/3 of the gas molecules are moving all three directions which is parallel to these three coordinates x, y and z axis. So that on an average 1/6 of the molecules move parallel to any one axis. If you consider x axis, means that is 1/6 of all these gas molecules are moves parallel to a particular axis. Therefore, the number of molecules, so here we write the number of molecules, crossing the plane LM upward or downward per unit area per second is equal to, that is n C bar divided by 6. How many number of particles are crossing to that of plane upward or downward of that of LM, that is n C bar divided by 6, whereas 1/3 of the particles are moving x directions, z directions and y directions parallelly. But if we consider each of that of coordinate axis, then it will be 1/6 of that of total molecules. So here the number of molecules passing the plane LM upward or downward per unit area per unit second will be n C bar divided by 6. Let V be the velocity of the molecules along the plane LM. Here let the particles having the velocity will be let V. So we write let V, that is the velocity of molecules along the line LM, and its differentiation dV with respect to dz, dV by dz, that is the velocity gradient velocity gradient measured in a direction from CD to AB, from CD to AB, that is perpendicular to LM. Then the velocity of the molecules of the gas along that of CD will be how much? That is dV by CD is the velocity gradient that measured, that velocity gradient is measured in a direction CD, in direction from CD to AB, which is perpendicular to LM. Therefore, the velocity of gas along the plane CD will be how much? That is V plus lambda times of dV by dz. This is the velocity of the gas along the line CD. And again the velocity of the gas along the line AB will be how much? That is V minus lambda times dV by dz. This is the velocity at LM layer. The velocity at CD, that is V plus lambda times of this much, and velocity along AB, that is V minus lambda times of that much. And lambda will be the distance, that is the distance between LM and CD, that is the lambda, and here the distance between L and AB, that is the lambda. Lambda here is the mean free path. So here write velocity of molecules of gas along plane CD is equal to V plus lambda into velocity gradient dV by dz. Similarly, velocity of molecules of gas along the plane AB is equal to V minus lambda dV by dz, where lambda is the mean free path, that is the distance between the planes, that is distance between LM and CD and distance between AB and LM. This is the mean free path. Let the mass of the molecule, let the mass of a molecule small m, then total mass crossing unit area of plane LM, which is plane LM per second, upward or downward, is equal to, here is the number of molecules passing, that is n C bar divided by 6. So mass of a molecule will be m, so total mass will be m into that number of particles, so 1 by 6th m n C bar. Therefore, the momentum carried downward. Therefore, the momentum carried downward by molecules crossing unit area of the plane Lm per second from plane CD is equal to, that is 1/6 mn c bar v plus lambda dv by dz. This term into that term, 1/6 mn c bar into v plus lambda dv by dz. This is the momentum carried downward by the molecules crossing unit area of that of plane Lm from CD per second. This is the momentum carried, 1/6 mn c bar into v plus lambda dv by dz. Similarly, the momentum towards upward. Similarly, the momentum carried upward by molecules crossing unit area of the plane Lm per second from plane AB. The quantity 1/6 mn c bar into, that is v minus lambda dv by dz. So, this is the momentum carried downward by the molecules crossing the unit area of the plane Lm per second from CD, that much. This is the upward section. So, the net momentum transferred. Thus, the net momentum transferred downward per unit area of the plane Lm per second, that is 1/6 mn c bar into v plus lambda dv by dz minus, here is the plus term, then it will be the minus term. So, minus 1/6 mn c bar v minus lambda dv by dz. On simplification, that term, that minus minus plus, there will be 2 times of that term, second term cancel out, that is 2 times 2/6, that is 1/3 m n bar sorry m n c bar lambda dv by dz. That is the net momentum transferred downward for unit area of that of plane Lm per second. According to Newton's law, the force is defined as rate of change of momentum. Rate of change of momentum is the force. Here, according to Newton's law, the force is defined as the rate of change of momentum. Hence, the above expression as we derived here is a measure of force on plane Lm by upper layers. That is the force on that of Lm due to the upper layer. Since we are considering unit area, that force is termed as the tangential stress. So, here what we write? Hence, the above expression is a measure of force on plane Lm by upper layer. Since we are considering unit area, this force is same as tangential force as we consider unit area. So, this force is same as tangential stress. That is the tangential stress. Therefore, the coefficient of viscosity eta is equal to tangential stress to that of velocity gradient. Here the tangential stress, that is 1/3 mn c bar lambda dv by dz, that is 1/3 mn c bar dv by dz divided by velocity gradient dv by dz cancel out. We have 1/3 mn c bar, here is the term lambda here, mn c bar lambda, a term lambda here. So, that is mn c bar lambda. This is what? That is coefficient of viscosity eta. We know the expression for mean free path. So, value of mean free path is put here, or eta is equal to 1/3 mn c bar into 1 by root 2 pi d square n. As we know, mean free path lambda is equal to 1 by root 2 n root 2 pi d square n. This is the expression for lambda, root 2 root 2 pi d square into n. That is the expression for mean free path. We put the value of lambda here. Now simplifying it, we have eta is equal to m c bar divided by 3 root 2 pi d square. This is the mathematical expression for coefficient of viscosity. From this expression, that is independent of pressure. So here from this expression, here the coefficient of viscosity is independent of pressure. Since the expression contains c bar, which is proportional to, we know c bar, that is the average velocity, proportional to under root of temperature. T is the absolute temperature. That is why the coefficient of viscosity, hence the coefficient of viscosity directly proportional to the square root of absolute temperature. Means with the increase in temperature, there is an increase in the molecular interchange between the adjacent layers as molecules move faster in higher temperatures. As a result, the opposing force also increases and a greater force is required to maintain the constant velocity. Thus, with higher temperature, the viscosity increases in gases. That particular expression indicates absolute temperature, which is directly proportional to the average velocity. This is the expression for coefficient of viscosity. So, with the help of this video lecture, we understand how one of the transport phenomenon, that is viscosity, which is the transport of momentum, that occurred in case of ideal gas. So, here we mathematically analyze how viscosity phenomenon for transport of momentum. This is the mathematical expression which is independent of pressure but depend upon c bar, and that c bar also depend upon that of under root of absolute temperature. So, finally, we conclude the coefficient of viscosity is directly proportional to the square root of absolute temperature. So, with this useful and informative notes, let me wind up this session. Thank you.